Welcome to Vintage Computer Festival, second day after lunch, I hope. My name is Guy Fedorkow. I am here to talk about a project we've been working on for quite a while, centered around this machine called Whirlwind. We'll talk a little bit about what the machine was, and what we're currently doing about this stuff. The starting point for this particular talk is what I've been calling an interpretive model for the machine. I wanted to produce a way to help people have a little bit more visceral feel for what it was like to actually use Whirlwind. And along the way, most people say, "Whoa, glad I'm not there," because compared to now, it's pretty tough. So let's start with what is Whirlwind. It is a machine that was designed at MIT. It executed its first instruction in about the end of 1949. It was not the first stored program digital computer. There are others who claim that, depending on who you want to argue about with what. But it was pretty close to the beginning. EDSAC was only a few months ahead of Whirlwind for operation. It began during World War II under a contract from the Navy. Their original goal was to write a flight simulator to be able to simulate aircraft that didn't quite exist yet. So they wanted to not only the usual trainer thing, but also to use it to try out design changes before they actually built the airplane. So their goal was a fairly complicated set of mathematical equations required to simulate aircraft flight. The project evolved as these huge research projects often do. They did some work on air traffic control, and the program and project ended up mostly working on what you would call the air defense problem. That is, how building a system that would defend the continental U.S. against the bomber over the pole threat. That evolved into a thing called SAGE, Semi-Automated Ground Environment, which was a humongous Air Force program that spread computers and radars across the country to network together to produce a system that could monitor the entire continent and marshal defenses against whatever might come over. And that work took up most of the Whirlwind time after the first 2 years. The machine is 16-bit parallel architecture. At the time, everyone else was doing serial, but these guys knew that they had a lot of calculations to do, and they wanted a fast machine. So I think at the time, this would have been, by quite a margin, the fastest computer around. It came with a 2K address space limit. We all know what happens with that. 3 years later, it was, oops, that's too small. But, tough, you're stuck with it. The machine was capable of about 50,000 heads per second, which, again, at the time was pretty quick. One reason that Whirlwind is often remembered now is because of the development of magnetic core memory. As a stored program machine, of course, they all knew that if they couldn't get reliable memory, then they could not make a reliable computer. They started out with electrostatic storage, the CRT specialized CRT tubes to store bits on. But neither, in spite of the fact that the Whirlwind team spent a lot of money on literally developing their own storage tube technology, nobody could make it reliable enough. Right? IBM used the Kilburn Williams tube, and it was okay enough that they could sell 701s, but everyone knew this was not going to work in the long run. The project lead, a guy named Jay Forrester, took a couple of guys to the back room, and fortunately they could afford to send them there and just don't come out until you think of something better. And what came out, of course, was magnetic core memory, which obviously had an impact on the industry, right, for decades. This was always intended as a research project. There was never an attempt to, even an attempt to commercialize Whirlwind. It was a one-of-a-kind research machine, and they knew that from the start, and they were fine with that. Thank you very much. By the time I got to Sage, of course, it got to be a pretty big project, and that was no longer research, but it was also not a commercially viable. It wasn't intended to be a commercial machine. At MIT, as long as they had the thing there, the contract with the Department of Defense reserved the good hours for DoD workers. And, okay, there's another shift in the middle of the night, and if you MIT guys want to use it, then go ahead. So they had a long line of researchers at MIT and other places who were interested in solving mathematical problems of all sorts. So there's a very broad range of things that got run on this machine, even though its purpose, according to the people who were paying for it, its purpose was air defense and simulation. And it stayed in operation at MIT until 1959. The architecture of the machine is fairly straightforward. It was, and for a modern computer architect, relatively familiar. Right? It's a single accumulator machine. There was an extension to the accumulator so they could do multiplies. Then a couple of other registers, the program counter, program registers, the instruction register, and then an I/O thing, and then a single 2,000 word memory unit, and a boot ROM built out of 256 toggle switches. So if you didn't like the boot ROM today, you could go flip the switches and have a different boot ROM. They did end up with a lot of I/O devices attached to this machine because of its nature as a real-time computer. They wanted to attach it to real stuff, which ultimately ended up with radar stations interfaced to it, and a graphics system was built in right from the start. They invented the so-called light gun, and a bunch of other stuff. I always think, in looking at that black diagram, I remember that during the Whirlwind project, there was a junior engineer named Ken Olson and another one named Harlan Anderson working on Whirlwind. And Ken kind of got frustrated a little bit with all of the bureaucracy involved with the Department of Defense and with IBM, and said, I'm out of here, I'm going to do this better. And we got DEC, right? At the same time, the Air Force, for very good reason, arranged a not entirely harmonious marriage between MIT and IBM to build Sage. And that was at the time when IBM was starting in computers. But it was also, they already had the 701 mostly designed, but but it was also the time when they were thinking about the 7094 and starting to think about the 360 architecture, right? So the fact that that diagram looks kind of familiar, I think, is not an accident. Right? We're still living with it. There was only one Whirlwind, but it's still with us, in my opinion. Okay, the I/O system, there was the usual stuff with a teletype-like machine. Paper tape was the medium of choice until they started to work with IBM, and then, oops, what do you know, there's a card reader. Mag tape drives, they did attach to drums. That was the furthest they got in mass storage, and at one point ended up with a line printer and stuff. The not so usual stuff, the control room for this machine, of course, had hundreds of lights and buttons just to debug the machine. But beyond that, they had more hundreds of buttons and switches and lights that were specifically made for operator panels. Right? If you go look at the Sage display here, you'll see what a Sage operator was faced with was usually a big CRT and a lot of buttons and lights. Right? And that's how computers were meant to be used in this day. So that's what they did. The machine was designed from the start with a graphics system. It's quite straightforward. It draws vectors, points, and lines on a CRT. They use big radar scopes with long persistence phosphors. So they intended from the start to be able to have graphical output. And I think, of course, if you're building a flight simulator, you got to have a picture of what's going on, right? So yeah, the pilot interfaces with buttons and lights and knobs, but you want to see what the instruments say. If you wanted hard copy, no problem. There's a camera. There's an instruction which says open the shutter. There's another instruction that says close the shutter, advance the film. So if you want to do a core dump, you draw the image on the CRT, take a picture, and get them to develop it. Right? They invented this thing they called a light gun, which quickly evolved into what I think of as the less threatening light pen, which of course eventually turned into a mouse. So there was a kind of point and click interface even in 1955, right? And I want to be careful about that because this was definitely not a point and click computer, but it did have the initial beginnings of that concept, right? See something on the screen, point at it, make it happen. And of course, they had to develop modems to connect the computer to radar equipment, miles away. Right? It happened that Whirlwind, of course, never moved. It was in Cambridge in the Barter Building on Mass Ave. And gosh darn it, there didn't happen to be an Air Force radar station right there. So they linked it by phone lines to a small Air Force base just outside of Boston. And conveniently, the Air Force Cambridge Research Lab, no surprise, was across the road from MIT. So, they kind of collaborated on getting all of these weird interfaces to work. Okay, the machine itself, the computer itself is kind of big. People say, "Oh, are you going to build a new Whirlwind?" I said, "No, we do not have a building to put it in. Thank you." The computer part of the computer was about 2,500 square feet. This is a layout of the actual CPU. The accumulator, the data path, essentially is 16 racks full of the stuff to make up the adders and the adders and the registers and so on. So it's effectively a bit slice machine before anyone knew what that was, except that the slices were racks instead of pieces of a chip. You can actually see one of these racks on in the permanent exhibit here. You see them. Obviously, all done with vacuum tubes, right? This was before there was such a thing as a transistor. The next row was memory systems. So they started with electrostatic storage tubes, which, in spite of everything they tried, couldn't get quite reliable enough that this row ultimately got changed to the initial core storage units. And then there's some other stuff. The control room, I always think if you were doing a Cold War secret laboratory movie, you would definitely want a thing like this in it. So not only is it where the start and stop buttons are, but also every other button, switch, and light that you might need to debug your program, because there was no GDB. So if it didn't work, you go look at buttons and lights and try and figure out what the heck went wrong. That also is the one of the display tubes that they used for the graphical output. This one is sort of the artist's view of how the system went together, right? The control room and the machine room that we looked at. Okay, so the graphical output on tubes like that, the radar tubes with long persistence phosphor, they invented this light gun thing to point at point dots on the screen and select a thing. This is the version that IBM did for Sage, and there's one of these sitting out on the floor also. I always use this picture to say, why did the Air Force make IBM and MIT cooperate on Sage, right? That's the answer. That's a science project. That's a product. You can tell. IBM knew how to make stuff. And MIT, of course, being unconstrained by that, knew how to innovate stuff. So they didn't like each other very much most of the time, but I think eventually came to recognize that this was actually a good idea, right? So once Sage took off, IBM was doing all of the production work, and MIT retained some control over the system design. You can tell that because MIT spawned Lincoln Labs in about 1953, which is, of course, still there and part of MIT. But then that split again into MITRE, MIT Research and Engineering, which is an independent federally funded agency that was created to complete the Sage program management, the program management of Sage. Again, so in spite of the fact that this machine was one of a kind, it really had a lot of impact on stuff that came after in a variety of ways. The Sage program would have been the biggest software, by far the biggest software project ever at the time, right? It employed thousands of programmers at a time when there weren't very many of them, and consequently, MITRE and the various organizations around Sage developed ways to train programmers, to make programmers as well as to make computers. The graphical system, I'll just spend a moment here, is very straightforward. You take a computer, you attach 2D to A converters, you attach a bunch of digital bits which flip the Z-axis on and off. So if you want to draw a point, you set the X and Y, you blip the Z bit, and you get a point on the CRT. So you can drive quite a few scopes if you want. They have to draw kind of similar images, because otherwise you'll spend a lot of time going from one to the next. But as long as the images are simple enough that you can keep refreshing them, then you get a very effective and very inexpensive, quote, inexpensive display system without any of the complexity that we're accustomed to with frame buffers and all that kind of thing. This also works. This is a bit of a subtlety, but this works with the light gun idea, because the light gun is just a photocell, right? And this took a while to get through my head, that a mouse tells you where you are, but you never know quite when. And the light gun tells you when you drew the point, but it doesn't know where, right? So when you are programming this machine, you program it to draw a spot on the screen, and you go check the light gun. Hey, did you see that one? Nope. Okay. Go on to draw the next spot. Did you see that one? Yep. Say, oh, okay. I guess he hit that button. Right? So it is inherently dependent on the very tight timing between the instruction that draws the dot and the light pen that sees the dot in order to tell what it is that it's seeing. The kinds of displays that you can create with Whirlwind are pretty straightforward, because you gotta refresh it pretty often, or else it starts to flicker. And depending on, so you get a trade-off between how much flicker you can tolerate and how complicated an image you want. This is an example of a game that we recovered from one of their tapes. It's a game of blackjack. This is, most of the demo programs were intentionally written as demo programs and are, have some form of documentation because they had a continuous stream of VIP visitors who had to be impressed with what they were doing with their $3 million. This game, the tape says blackjack on it, but there is not a single clue as to where it came from or how it happened. I'm sure that it is a 3 a.m. operator, I am bored project. But it does play an effective game of blackjack, and it uses the light gun, right? So you can use the light gun to hit a hotspot to say, I want to play this card. I want to stand. I want to hold. I want to change the meaning of an ace, all that kind of stuff, or reset the game. So, but this is the kind of thing that you'd expect on a display from Whirlwind. You can't do too much more complicated than this, or it starts, again, the flicker gets worse because it takes longer to draw the thing, and you got to refresh it all the time. Okay, so what are we doing here? We discovered a few years ago that CHM has 1,000 tapes from Whirlwind, paper tapes and magnetic tapes. MIT has about 2,000 documents from the Whirlwind project. We didn't know what was on the CHM tapes. You say, pile of documents, pile of tapes. Maybe we can figure out how they fit together, right? And learn something about programming in this day. As we said earlier, there are some physical artifacts left. Most of them are here, but only about 1/3 of the machine still exists. Most of it has either was completely destroyed or else distributed into who knows how many desk drawers and back offices, and there's a piece on display somehow at Stanford. They turn up all over the place, but mostly destroyed around 1970. So, of course, the question is, how do we use all this material to learn something? So why are we doing this? This particular project with the interpretive model, obviously, we're not going to build another Whirlwind machine. The guys in the UK are building an EDSAC replica, which they're trying to get accurate down to the connection, tubes and all. But EDSAC was a much smaller machine. It would easily fit in this room. Whirlwind, no. It's simple, no is the answer. 10,000 tubes, 100 kilowatts, thousands of square feet, it's easy, no. But a Python emulator running on an ordinary Raspberry Pi runs at about the same speed as the real thing. And since we're interested in recovering the software, that's fine. That's all we need. What I wanted to do with the model, and of course I can do that on a laptop and do most of the time work on this on a laptop. The thing I wanted to capture here is that the user experience for this machine is quite unlike anything we do now, right? It was focused on this idea of buttons and lights and a very simple graphical CRT. So what I wanted to do is put together something that would give you a little bit of a feeling for what it was like to actually use the machine. And thank God I don't have to debug stuff on this model, although it's possible. So the model then is based on replicating their view of the priority of what kinds of I/O devices they wanted to have. Okay, the actual operation of the machine, we do have some documents that describe how to work it, you know, sort of the meant for the operators. There's an interesting quirk here that this project is sometimes credited with inventing the vocation of computer operator, right? That when they started, it was all engineers and programmers of various sorts, and the Whirlwind guys kind of liked organization a little bit, so they thought, really we need, the machine time is really very costly. Let's try to optimize this a little more carefully, and they discovered they could hire guys who had technical knowledge but weren't going to make it through engineering, and they actually made pretty good operators, right? And in fact, the first operator that was hired was a very bright guy who grew up in Boston, was in high school in Boston, and happened to be black, right? And so, as you can imagine, he was going to have a tough time getting through engineering, but in this job, it was great. It was a perfect match. So a new vocation was created. So to help operators, there were some instructions. The project had a photographer who took thousands of pictures of just about every kind of image you can imagine, from PowerPoint like view graphs, through to photos of, a lot of photos of dignitaries and so on. Many of them were taken in the control room, but there aren't many pictures which were intended as documentation of the control room. So we only have kind of incidental views, and they kept changing around anyway, so it's really hard to tell what was there wasn't a definitive control room, but there was a lot of stuff that carried through all of the iterations. So we have a good idea of how the thing worked and how it was run. And CHM's collection has some of the components that were in the control room itself. I always have to say at this point, the Smithsonian got first crack at the artifacts from when the machine was finally destroyed. And I'm sure they got the good stuff and went and pushed it into a warehouse somewhere that no one can see it anymore. But there is most of the material here is at CHM of the remaining bits and pieces. We came across this object, this unassuming object in the CHM collection appears to be the actual central control point for the machine, right? So the row of buttons along the bottom here is fairly obvious. It's the start, stop, single step, the kinds of things that you would use to actually cause the machine to begin executing. There's a button that says, go to the tape, hit the bootloader, go to the tape reader, read in the tape, and run it, please. So that's the starting point for control of the machine. This big red light is, hey, you got a trap. You have stopped. you better go figure out what went wrong. The second part here is how do you tell it what you want to do? There were these two registers which they called quote manual intervention registers, and they are just general purpose registers in the machine, but their conventional use is one of them was used to, like, these are radio button things, right? So each one is one 16-bit number. The conventional use is that the right-hand one sets which program you want to run out of the set that they felt were kind of common and that lived on the drum. And then the left-hand intervention register was used to enter the first level parameter for the program. So, if you want to run, one of the demos I use a lot is a simulation of a vibrating string, right? And there were a bunch of different physical parameters that you could adjust to tune how stretchy the string is and how many points there are on the line and all that stuff. So you can input the parameters that you want there and set the number and then say, go do it, right? So that's the primary mode of interaction with this machine. The secondary mode, and this is a little hard to believe in retrospect, but they knew from day one they had a problem with memory, right? Von Neumann architecture, if you don't have reliable memory, you don't have anything. So during the development of their electrostatic memory, they rapidly built the ALU, but they needed something to run. They had the 32-word toggle switch boot ROM, which you can fit a lot of different things into 32 words, and they had 5 so-called flip-flop registers. That is 5 read-write memory locations made out of vacuum tubes, and that took a whole row of the computer room. Those served initially, of course, to provide a way to debug the machine, but they survived long after that as a generic input-output mechanism. You could preset the flip-flop registers to whatever number you wanted, and you could see the results as they were updated by the machine. So these 5 flip-flop registers turned into another generic I/O mechanism for the machine. So a secondary way to input parameters and output results. Interestingly, they were fanatic about reliability, so every bit was 2 lights, and we can take a poll at the end whether you would make red light a 1 and a white light a 0, or white light a 1 and a red light a 0. I think the evidence at this point is pretty clear that they chose red light as a 1 and white light as a 0. I don't know why, but that's what they did. So it does represent one 16-bit number in 32 lights. And I think their point was they weren't completely confident that flip-flops would flip or flop. And so if you saw either dark or both lights on, you'd say, uh-oh, time to call the hardware guys and say, what's the matter with that flip-flop? This is where I really wish the photographer had spent more time taking documentary photographs of the control room, but this was a black and white photo of the thing and the initialization switches that went with it. One of the let's say interesting things about this kind of archaeology is Whirlwind, of course, went through a variety of unhappy circumstances and ended up at DEC in their original computer museum. And oh darn it, someone at DEC, I am sure, decided we need a blinking lights display using this. So they took the Whirlwind stuff, these panels, quite a few of them, and modified them to have modern drivers on the back so that they could connect them to, I assume, a PDP-8 or something and make it blink all the lights. So in fact, there's a layer, there are two layers of restoration here. Right? Layer number one is what's in the museum, which I think represents what was in the DEC lobby, but you can see underneath this nice clean black label there is the original label for whatever this register really was at the time. So this one, although it says it's flip-flop register number 3, it probably isn't. And we're not going to pry off the label to see what's underneath it. My guess is that the real one is in the Smithsonian collection that we can't go see. Okay, what's with this model? This is the thing that we're talking about here. What I wanted to do was kind of try to capture the essence of this machine in a thing that I could put in a briefcase instead of requiring a moving truck. So what we have then is one copy of the manual intervention register and a pair of switches to flip back and forth. 2 of the 5 flip-flop registers and the presets to allow them to be preset before the program runs. The set of controls along the bottom is pretty close to what the original one had for start, stop, reset, single step, breakpoint, so on. So that this is actually fairly accurate. And then a subset of the CPU registers, the essential things to debug a program, including, of course, the memory address and data and the accumulator. There's only one, thank God, and then the program counter. This also includes the graphical stuff to, the graphical driver to drive an analog oscilloscope. So with that, you can run more or less the same thing that, it in a similar way to the way the real machine would have been run. They didn't exactly have, nobody had an operating system as such. It was, programming was essentially bare metal. But by the late 50s, they had developed a program, what they called a program director, a utility that would monitor the manual intervention registers and would go to the drum to get stuff to load and run. We've recently come across a few source files that look like they form this utility control program. I haven't got them working yet, but we'll keep chipping away at that. In the meantime, I run a small program that is a combination of Python and Whirlwind code that emulates that function. So to run a program assuming it's one that is on the quote drum, you use the radio buttons. The radio buttons to select the number. You can change the program parameters if you want, and then press the activate key, this button here, which says now go do it, and that will load the program and start it executing. A kind of a curious quirk is that there doesn't seem to be an official Whirlwind way to stop the program. You can stop the computer, but I think what you're supposed to do is stop the computer and then jump back to the boot ROM and start it again with the utility program. So there's there's no convenient mechanism to say, I'm done now. Could you, like, give me my executive back? But, okay, that's life in the BARDA building. So of this recovery work, we have recovered a bunch of tapes. The ones that are listed here are mostly, there are a few listed here that are new Whirlwind programs that, or programs written in Python specifically to demonstrate something. But a number of them are actually original Whirlwind code, just in the good case, in most cases, literally read off the tape, transformed into a core file and then run. Right? So some of these are, many of these are demo programs, because of course they had to have them ready and they had to run fairly easily, because suddenly General someone is there. Oh my God, load the tape. Some of them this one is a quirk. It's very straightforward piece of code. It has its action is perfectly obvious. We have no idea what it's for. Right? It exercises the CRT and the light gun. And my theory is someone was working on the front end for another game and they didn't attach the game part to the back end. So we've already talked about the blackjack game. There are a number of test programs. There's quite an extensive diagnostic suite that I don't actually have running yet. A couple more demos. There's quite a complicated game of NIM, the token removal game. Typically viewed as a game you play with a pile of matchsticks and remove, and whoever takes the last one according to the rules wins the game. This is for some reason they did quite a bit of work on this, and it's quite a sophisticated extension of the normal game of NIM. That one also does run. I think the most significant piece of code that we've recovered is also the hardest one to demonstrate, but in 1951 they actually started on this air defense work, and to convince the Air Force that they knew what they were doing, they ran this large-scale experiment of connecting Whirlwind to radar stations, tracking actual aircraft, and running, games, if you will, of designating one guy as the target and another guy as the interceptor. And then Whirlwind would monitor the radar, would figure out who was who according to what the operator was doing with the light gun, and then continuously compute a heading to transmit to the interceptor pilot to bring about an intercept. Right. So the operator would designate the two aircraft with their appropriate tasks. And in one of those light registers, then Whirlwind would display in BCD, binary coded decimal, would display the heading that the interceptor pilot should fly. And these were servo mechanism guys, so they knew what they were doing, and they would track the velocities and so on, and continuously update the heading to the interceptor pilot. I'm always amused that during the demo, the Whirlwind operator was expected to read the BCD off the lights and talk on the radio to the pilot. Say, dude, fly 303. And from the Whirlwind guy's point of view, if they got the interceptor within a mile of the target, then, hey, we're done. See ya, gotta go now, and head out for a beer. So the demo itself is hardly compelling. It just to understate it, it's it shows a replica of it shows what Whirlwind sees from the radar system, and so it tracks as the planes move, but that's about all you see, right? A couple of dots moving across the screen, and if you're lucky, they come close to each other, and then things get confused because it doesn't know which one is which anymore. So we have run the code. We can run the code. It's not a very good demo if you don't have real airplanes flying around. For the Air Force officers, it must have been just astonishing, right? That thing is telling my pilot how to get to, holy cow, right? So obviously it worked well enough to sell them on a Sage. And then we have a couple of other things that are just there for, to demonstrate the graphical system. The NIM game is a good example of the challenge of using Whirlwind of the user interface that they were accustomed to. It draws the state of the game on the CRT. So as you might know, when you start a game of NIM, you start out with a bunch of tokens in a bunch of buckets. And you tell, and to play the game, you say, I will remove up to a number of tokens from a bucket. So the way it is played is that there's quite a complex initialization scheme where you have to step through the buckets and enter the number that you want in each bucket using these manual intervention flip-flop registers. And then once that's done, then you can start playing the game again by hitting on the radio buttons the group and the number of bits, number of tokens that you want to remove, and then you tell it to play its move and go back and forth. So the game does actually work, but it is challenging. I mean, it's tedious because of the interface, in my opinion. But that's what they had, so they worked with what they had. We talked about this radar one a little bit, just add a bit more. There is a document dated December 1951. David Israel is an interesting guy. He worked on Whirlwind. He joined the Whirlwind project at the end of his bachelor's at MIT. I think he got sent off to World War II for a little while, but came back to MIT and finished his degree, went on to do a master's, and stayed with this idea of using computers to keep track of airplanes. So his first task at MIT was air traffic control. And I always think this is amusing. His job there was to make sure that airplanes did not crash together. Keep them apart, please. He rapidly transitioned, as the project did, to the air defense problem, where, of course, you just flip the sign bit. His job was to make sure they did collide. Thank you very much. Of course, it's not quite that straightforward, but I think the change in perspective between don't let it happen and do let it happen was kind of an amusing career twist. So he stayed with this problem of using computers for the air defense problem all the way through his career. So he stayed with Whirlwind, then Lincoln Labs, then Sage. And it's interesting in his oral history notes at the Smithsonian, he says, yeah, well, you know, sometimes they gave me a new badge. Yeah, sometimes they gave me a new office. I don't care. I just did the same job, you know, the whole career. So he was pretty good at this. His document, I wish there were more David Israels. If you look at the outline of the document, you'd say, nice functional spec. Thank you very much. You know, it outlines the problem and how to solve the problem. It gives you a block diagram for the code, works through some of the hard parts of the code, and then it gives you the entire corpus of the code, which I may have said only 5 times so far. This initial air defense demo fit into 256 words of storage, complete with the graphical display and the light gun and the navigational computations and the lights and all the rest. It's astonishing, and it is a very challenging piece of code to debug. Yes, I think we talked about this. The actual flight tests they would have planes in the air under MIT's control. MIT had the instrumentation lab, which did a lot of work on aircraft stuff. So I hadn't quite grasped this, but MIT actually had airplanes for doing this kind of testing. I assume they were owned by the Air Force, but they were designated as MIT's for MIT's use. And so they would do flight tests with a couple of attackers and interceptors. And the display, as I said, is singularly unimpressive. That the dots representing the aircraft move across the screen. The ones that Whirlwind is tracking would have been displayed on a second display. This is where the ability to draw similar drawings on 2 CRTs with slight differences was really helpful. Right? They could put all of the stationary stuff on both CRTs and then move the tracked aircraft from the radar images, move them separately so you could see whether they were really tracking properly and so on. Okay, so let me wrap up. As we go forward on this, there are still a lot of tapes to sort through. I know there's one that we recently got working, again, is not very demo friendly, but one of the first algebraic compilers was written on Whirlwind, done by a pair of researchers named Hal Laning and Neil Ziering. That compiler we actually have running. It was intended for doing solving algebraic equations on a machine. So you could type in equations and it would do Runge-Kutta integration and so on using subroutines built into the interpreter. So we recently got that one working. There are quite a few more things like that on these tapes, and we're gradually chipping away at them. A different thing, a different angle on this. I am still looking for. I haven't done a lot of work on this. I'm still looking for a good way to hook the physical model. Of course, is fine as long as you're there in front of it, but most people aren't. So I'm looking for a way that I can make this stuff usable through a web interface. Right? It's not that hard. Just it's not my thing to do. So I'll keep looking. If someone knows a great way to make an interactive Python program visible through a web browser, let me know. Interested. Ken Sharif here actually translated some of the code into JavaScript, which is quite effective in a web browser, but I don't want to do the whole environment. So we're still working on that. Again, with the goal of making this all more accessible so that you can do it yourself. You can download the simulator if you are familiar enough with Python. It's not that hard, but it's kind of a hassle. And with that, oh yes, this is the the official decommissioning of Whirlwind in 1959. We're not actually sure how this photo came about. Obviously, the pin did not get pulled. No attractive models were hurt, but it is a reminder of the focus on the military kind of application and culture that they were immersed in. So with that, with that, I'm supposed to show this Spark QR code, but over there are some URLs for stuff that you might find interesting if you want to follow up further. And of course, if someone wants to know more about it, contact me. It's not that hard to do. Can I ask if there are questions?
Any comments on the effectiveness of the UI experience?
Yeah, their light gun was so CHN has a couple of them, right? There are a number of them in the half a dozen of them in the archive. No one has ever tried to activate one. I don't even know really what's inside one, but it must have been an extremely clunky device to use. The gun physically is quite heavy, and the focal spot on the end of it is very small. The barrel of the gun, as you saw from the photo, is quite large. So you had to get it lined up just right. It actually had an optical sight, so you could look through the sight to see what the gun was pointing at.
So there's no feedback loop. It's not going to buzz, or it's not going to.
I came across this just recently looking for something else. Somewhere, I think probably about 1953, someone said, this is kind of hard. What we're going to do is add a, quote, chime. So if you hit the thing and it actually hits the right point, it'll ring a bell of some sort. I don't know what it was, but something that made a noise. I haven't tried to emulate that little piece yet, but that was their response to it. The Sage light gun, I think, was much easier to operate, although we talked to a Sage operator who recalled that that was not a lot of fun either. I mean, it was still challenging to use the light guns effectively, even on Sage.
Do we have any idea how often it was actually used? In other words, how in real life, how often would an operator have ever actually pointed at something and said,
"Oh yeah." So in the air defense demo, whoops, let me back up the right place. Yeah. So here, the step before this, the screen, the real screen, of course, was just monochrome, right? But the radar display would have just shown the three, however many aircraft there were. The way to work it is the operator would then use the light gun, point at one of these images, set a switch to say, I'm going to select the attacker, click the gun on the attacker image on this dot, then flip the switch to say, I'm going to designate the interceptor and go point the gun and pull the trigger here, right? So that was the way it was used. It was never used, as far as we can tell, in the way that we would expect with a mouse kind of thing of, pick option A, option B, none of that, right? It was, but it was definitely used for interaction with the radar system.
Hope you don't get them mixed up.
Well, that's what radar operators are paid to do, not get them mixed up.
I really hate to interrupt you, but we got people outside who got the next speaker. You're exhibiting, correct? You're on the floor?
Yes,
So if
Yes,
anybody
sir.
has questions, you can find them, but you're also welcome to talk out front.
okay. Well, thank you all very much.